Hi everyone, my name is Hezi Zhang. I'll be presenting the paper 1Q, a compilation framework for photonic one-way quantum computation. Photonic platform is a promising candidate for quantum computing due to its great scalability and easy integration with quantum networks. But it also brings unique challenges. For example, the weak interaction between photons makes multi-qubit gates much harder than other platforms. On the programming level, one-way quantum computing, or measurement-based quantum computing, has been identified as a suitable computing paradigm, as it doesn't require multi-qubit gates but only one-time single-qubit measurements. However, few attempts have been made on the compilation side to deal with realistic hardware constraints. While previous work can provide a basic interpreter from the circuit model to MBQC with the help of a cluster state, this approach is inefficient to scale it up on hardware. Practical photonic hardware scales up by generating a lot of small entangled states called resource states and combining them into larger entangled states via fusion. Our insight is that generating cluster states by fusion would cause unnecessary overhead, as a lot of entanglements in the cluster states are actually redundant for the computation. To minimize the overhead, we should generate only the necessary entanglements, which can be represented by graph states. Our contributions in this paper can be summarized as the following. First, we abstract a practical hardware model and formulate the problem of compiling graph states onto photonic hardware. Second, we identify critical compilation challenges caused by the dynamic generation of resource states, the low degree of nodes in the resource states, and the irregular geometry of graph states. Third, we propose a compilation framework to tackle the challenges with three optimization modules: graph partition and scheduling, fusion graph generation, fusion mapping and routing. Last, our framework outperforms the basic interpreter by orders of magnitude in terms of execution time and resource consumption. In this table, we show the experimental results. As photonic qubits are generated in layer over time, the first metric is that we want to consume as few layers as possible. Since fusions are the most error-prone operations in the computing process, the second metric is that we want to minimize the number of fusions. It can be seen that 1Q achieves significant improvements in both the metrics. Furthermore, it achieves the same levels of improvements for resource states of various structures, such as the line-shaped, star-shaped, and ring-shaped graph states, which shows the generality of our framework. Thank you for your time and attention. I invite you to listen to our full talk and read our paper for more details.